them at the moment.
Are you?
I've got sinusitis.
You need to watch this,
Which is why I sound a bit funny, if you're wondering.
You always sound like that, love. Since the 1800s, scientists like Louis Pasteur have contributed to our understanding of, where they come from, how they work. And in 1928, Alexander Fleming discovered penicillin. Now, since then, antibiotics have gone on to save countless lives. But it now looks like we are running out of them. And if we are, our fight against bacterial infections could get very nasty indeed. Surgeons behind me are carrying out a routine hernia operation, and it's more than likely that this patient will have a full recovery with no complications. But it's easy to forget that less than 100 years ago, this kind of surgery would quite literally be a matter of life and death. In abdominal surgery, the risk is especially high, as the release of bacteria from the gut into the body is almost impossible to avoid. But thankfully, the development of antibiotics gave us the upper hand in the battle against bacterial infection, and the risk to life from something as routine as a hernia operation has been almost completely eliminated. Antibiotics kill bacteria either by damaging their cell membranes or by interfering with their reproduction. To obtain them, we've simply harnessed natural defensive substances released by fungi or bacteria themselves as they fight to outcompete other microorganisms. But it's a never-ending war, and the trouble is that right now, antibiotics seem to be on the losing side. Bacteria seem to always be one step ahead. Antibiotics will work for a limited time before the bacteria they're targeting become resistant. And then we have to go all the way back to the drawing board to find new, effective antibiotics. A single bacterium can multiply 200 trillion times in one day, and they mutate at a very high rate. So resistance can evolve incredibly fast, and some scientists predict we'll run out of antibiotics in 10 years. Tony Maxwell is at the front line of the battle against bacteria.
The more you use antibiotics, the more resistance you're going to get.
The more you're forcing them to evolve, to be resistant.
And one of the worst things you can do is take a low dose or a small dose of antibiotics, because the more bacteria can then survive. You'll get more mutations and more resistant individuals. So it's very important that one uses antibiotics at exactly the right dose and, as the doctor says, to finish the course.
So Tony, paint a picture for me. The world without antibiotics, what would it be like?
Right now, antibiotics are our best defense against bacteria. And we'd have the spectre of all diseases, for example, like tuberculosis, coming back. I think we could have a very serious problem of infectious disease. And I'm not talking about the developing world, I'm talking about the developed world too.
So if we face a future without antibiotics, what alternatives do we have? I've come to Cambridge, where Dr. Heather Fairhead has taken on one of our biggest threats, MRSA. And resistance won't be an issue with her solution: to attack the DNA of the bacteria using one of their natural enemies, a virus.
What we do is we use these bacterial viruses, or phages as they're called, we use them simply as couriers or a sort of postman to deliver an antibacterial agent to the bacteria. So our antibacterial agent actually kills the bacteria from inside. So here we have a culture of MRSA cells.
So that's MRSA in there?
It is, yes. Ooh. And that's been grown overnight at 37 degrees.
The perfect body temperature for them all to grow like the clappers.
Exactly.
Yeah.
By the morning, you can see this looks really cloudy, and that's due to all the MRSA bugs in there.
So what do you do with that then?
So to this, we then add a small amount of our antibiotic agent.
Grand.
And then after overnight, if you come back, the culture will have gone from that, which is just MRSA, to that, which has been treated.
That shows that all the bugs are dead, then?
Yes, basically.
It's amazing.
And on a Petri dish.
Yep. Without the agent?
Yep.
With? That's spectacular. What an amazing result.
And we can get that, say if that was 100,000 bacteria on there, we could get to that number within 5 to 10 minutes. So
it sounds hugely effective. Results like this are pretty impressive, but there's still a few years of clinical trials ahead before it's safe for public release. But it's not the only strategy. At Nottingham University, they're taking a very different approach. They're not trying to kill the bacteria, but confuse them.
Now, for many, many years, we thought that bacterial cells behaved as individuals.
Okay.
Now we know that, in fact, they are very good at cooperating and causing trouble as a group rather than as individuals.
Okay, so how on earth do they cooperate together?
Well, would you believe it, bacteria are basically able to communicate with each other. The term we use to describe bacterial coordination is quorum sensing. Here we have an image that's been taken over 24 hours with time-lapse photography.
Okay.
So each of the little bacteria in that spot are talking to each other, they're starting to grow, and then suddenly, bang, let's migrate all over the tissue.
There's this massive growth outwards and then another sort of wave of...
That second wave of activity is the production of all the toxins that the bacteria produce that help kill immune cells, white blood cells.
How are you using this knowledge of bacterial communication to combat infection?
Now, what does an army need when it goes into battle? Well, it needs to have strength in numbers, it needs to have good lines of communication so that it knows when is the best time to deploy your weapons. If you deploy them too soon, you'll get wiped out by the enemy. So each cell releases a small signal molecule and it can be heard by a receptor or receiver on the neighbouring cells. So we've been designing molecules that look just like the signal molecule, but are sufficiently different to stop the signalling happening. It's basically making it deaf. It's not killing the organism, but actually reforming it, stopping it, doing the bad things that lead to all the tissue damage.
How soon do you think we will have a very real drug to take to combat bacterial infections?
Well, we have the molecules that work in the lab. We need to refine their structures. It's probably still going to be of the order of 5 to 10 years.